نگاه کن مامان، میبینی رنگشو؟ تو هم یه نگاه کن ببین من درست میگم یا نه. نگاه
Hello. Hi, everyone. How are we doing? Can people hear me?
Yes.
Cool. Thank you. All right. Let me just get my chat window open and my screen shared. All right, we have 15 people. That's good. Let's all say hi to each other in the group chat. All right. Cool. Everyone's active. Everyone's awake. All right. Welcome. So let's begin. Tonight is the final night before your midterm. So there are several things we want to cover, but the focus hopefully is to solve problems. So there's sort of three things we can do. Number one is solve problems from what is voted for in front of me. So this is the current result. I see these four problems are very popular. Another option is to solve the practice midterm problems that we have not yet fully done in the discussion session. So that's another part. And I also want to give you some tips on sort of final review studying what you can do at the end. So but let's just start warmed up in problem solving mode first, right? Perhaps let's just start with these problems, right? So hopefully you guys just to follow along. Hopefully you have a notebook or some scratch paper in front of you. So I will, at some point I'll ask you to give it a try yourself as well. And if you have any questions, as usual, feel free to just type it out on chat or interrupt me. Yeah, all right. So, any suggestions, by the way, before we go forward? Does this sound like a good plan? Because I really want to tailor it to be able to help you guys.
So are these problems on your screen right now, the voted for? These are problems from the book?
Yes. Yeah, from the textbook. Yeah.
Okay.
Yeah. I'll pull it up on my screen side by side as well. But of course, if you have your textbook, yeah, you can feel free to follow along. Yeah, good question. Any other questions or suggestion? Does that sound like a good plan? Feel free to be active and either, yeah, just unmute and talk to me or talk to me on chat. Either way is fine. I like to, sometimes it's nice to go along and have some response. Just a reminder as well, the session is recorded. Yeah, so just to let you be aware of that as well, but don't let that stop you from being interactive and talk to me. Okay. My plan is let's start with solving let's start with maybe solving one or two first, just to get ourselves warmed up. I'll talk a little bit about different exam tips, and then maybe before I jump to the other two, we'll switch to do some practice midterm, or maybe later I'll give a poll and see what do we want. And then I'll let us decide by democracy, right? But yeah, all right. Without further ado, let's start first. This was voted for quite a long time, so I really want to do this first and to hopefully answer people who are struggling with this problem. So this is the wine bottle problem. If you had seen me solve any problems before, you know my approach by now. My approach is always start with drawing a diagram, state your aim, and then solve. So we'll go with that. So this is for reference chapter 17, problem 21. Okay, so imagine this is really, I'm taking the midterm. So on the left-hand side of the screen, this is probably what you'll see on the Canvas quiz. You'll see this problem. And on the right-hand side, imagine this is your scratch paper that you're actually, this is what you're going to do. Right? How I would go about, if you beat me to it, that's also great. I started with drawing the diagram. So I do it line by line to make sure I don't miss any information. Okay? So the first line says a wine bottle is never completely filled. Okay, so maybe I can draw a wine bottle, but let me read one more sentence to get a better sense. A small volume of air is left in the glass bottle cylindrically shaped neck to allow for the wine to expand. Okay, so basically this scenario over here, so I just need to be very rough. So there's a roughly cylindrical area over here before the wine bottles open up. So that part over here is cylindrical. Okay. All right, and it tells me, make sure I don't miss any information. The first information I was given is diameter. Okay, so the diameter over here. Here's one tip already: to when you label information over, don't be that lazy and not copy the variable over. Just a very minute extra effort, but it's very helpful. Okay, so copy D equals to 18.5 millimeters. Okay, you'll see why that is useful in a second as we go forward. So the wine has a large coefficient of thermal expansion. Good. Okay, so that's nothing new I need to draw or new information, numerical information that it's given. The distance h between the surface and the liquid content. Okay, good. So now I have a new information. It's the headspace height. is 1.5. Okay, so I'll copy that over. So this is between the liquid and the top, this is H, okay? And it's 1.5 centimeters. For a 750 milliliters bottle, okay? So the bottle here contains, so milliliters is volume, right? So immediately, if they did not tell me what variable it is, I need to invent one for myself. That will really help me to, when I set up my equations later on, it will help me to use the variables to set up. And whoever's grading your work, they can look at what variables it's written here, and then they can trace back to your diagram and see that, oh, this variable means that, because different people might use different variables. And if you don't have a diagram, whoever's grading it cannot see, cannot guess what variable that is. But if you have a diagram, that will be clear. This particular statement doesn't apply to our online exam, of course, because we're not grading a scratch paper, but general tip.
The professor mentioned that you'll be giving us partial credit. So does that imply that we're going to have to upload our work? Because I don't see how online we can get partial credit from a multiple choice question.
Oh, really? I was not aware of that. Yeah, double check with the professor what the procedure is.
I think she said that one question might have multiple parts, and you might be able to get questions for like points to those like separate parts, but not actually like partial credit for your work.
Right.
Oh, okay.
Yeah, so let's say like one question has multiple parts, you get partial credit by getting like, she basically breaks down one big question into several parts that it allows you to get some points.
Right, yeah, that was my impression as well, yeah.
Okay, got it, thank you. Sorry, you can continue.
Yeah, no problem, yeah. Yeah, feel free to ask any questions, yeah. All right, so volume is 750 milliliters. At this point, milliliters, I might as well convert part of it. I don't want to have too much like milli, at least you can go all the way and convert it to meter cube. So everything is in SI units, but or SI base units. But let's do partially first. And then where was I? Bottle filled at 20 degrees. Okay, so the temperature is 20 degrees Celsius. All right. So I have every information up to here so far. Due to alcoholic content, the wine coefficient expansion is double that of the water. Okay, so what you can do is on the side, you can also write out all the givens. Okay, so in this case, the beta of wine is twice that of water. Okay, and then in comparison, the glass can be neglected. Okay, the glass won't expand. Estimate H if, okay, so here estimate, so this sounds like an aim. The bottle is kept at 10 degrees and then 30 degrees. So let's do one at a time. So the aim, at least for part A, is to ask the new H. Right? So do not repeat a variable unless it is exactly the same as what's given. So with some practice, this should be very natural to you. As soon as you write down something that you've written before, write down a variable that you've written before, immediately pop up an alert in your head, ask yourself if that's the same variable or not. So that's not, okay. So the new height, okay. You can put a prime or anything fancy. You can put H1, H2, H initial, H final, H naught, H whatever, but anything that makes sense, that's good enough. Okay. Right, so we want to find this, maybe I'll copy down as well, then you'll hide at 10 degrees. So with a bit of practice, I think, or without my talking in real life, this whole procedure that you see in front of you should take maybe 30 seconds, 20 to 30 seconds at most. And then you can now, for this online exam specifically, now you can focus on your paper in front of you and sort of do the actual physics and not have to worry about number one, looking up and down, number two, digging for these numbers and values again in the very dense, long question. Okay? So as the real test, if I have translated everything on my paper correctly, is if I don't need to read the question again for the rest of at least this part of the problem. Right? So let's see if that is true. So, all right, when we solved this is what we talked about last time, when you got to this stage. So this is the part where I think And everyone should be able to do this. And it's a very good way to set you up for successfully solving the rest of the problem. Now comes the actual bit. As I mentioned last time, think of two things. Number one, think of any relevant equations. Number two, think of any relevant definitions. Okay, so definitions means if there's any especially tricky jargons or technical terms in the problem, you might want to first replace that scary term in some more down-to-earth terms so you can feel more comfortable to manipulate. Here in particular, I think everything is pretty simple. Volume, you know, height, diameter, beta maybe, but most of them I think we're relatively comfortable. There's no particular definitions we have to expand. So the relevant equation I think everyone already know is the volume expansion, because I think it's pretty obvious. This is where the starting point is. All right, but this is the point where so far, technically, if this is a paper exam in normal exam situations, even if you write down this formula, it won't score you any points. Remember, copying this advice applies mainly to paper exams, but still, copying a formula just from the formula sheet to your paper, to your working, does not score you any point if you don't apply it to the problem. Okay. Although it's not directly relevant to your upcoming exam, there's a reason why points are scored or not, because if you earn normally if you earn a point in a paper exam, usually you're going in the right direction, right? So when I say how you can earn partial credits in a normal situation, that means how you can progress successfully in the problem in general, right? All right, so let me repeat, you need to apply it to the scenario, right? So what is our scenario? Your question is, what is the delta V for? What's expanding? In this situation, there are several options. It could be the wine, it could be the air above the wine, it can be the glass. So I think it's pretty obvious it should be the wine, right? So apply it, wine, beta of wine, V naught of wine, and the change in temperature of wine. Believe it or not, in a paper exam, as soon as you write down this subscript, you at least get 1 point. This is the difference between copying the equation over without applying and copying over and applying. Okay? All right, moving on. Now you want to expand. Now that you found the equation that is relevant, the next step is expand the variables. Okay, so delta Vy means final wine minus initial wine, beta wine, this I don't have to expand. V naught just means initial. And delta T is T final of the wine minus T initial of the wine. Okay. Any questions so far? All right. As you see, the next step, I become a little lazy. I won't write out the whole word wine and just do W. That's also okay as a grader. For any TA, any teachers who's grading this, it's obvious what the W is if it's directly followed by the previous line. I think it's pretty obvious. All right. Now we come to the final tip in the solving bit. You found a relevant equation, you have applied it to the scenario, you expanded the variable. Now it gets complicated, right? It expanded out into a very long expression. So to manage it, to make it less scary, what you want to do is tick off variables that are known.
Did you get the point down?
Is that a question? Is there a question? No, okay. Yeah, so to handle scary equations, check off things you know. All right, so I know the initial of the wine. That means immediately I'm given this. I know the initial temperature, right? So that's 20 Celsius. The final temperature, 10 Celsius, and beta wine. All right, so this one would look it up, right? or usually it's given. Let me just copy it from the PDF. This is 210 times 10 to the minus 6 in base SI units. So base SI units are the MKS units, right? Meters, kilograms a second, the MKS. Right, that means I can now know the final volume of the wine. Good, right? So immediately I can find the final volume of the wine. Before I plug in the numbers, let's just move on with the concept first, because I'm sure you can plug in numbers and get that. The only tricky bit in plugging in the numbers is dealing with units. We'll circle back to that. So let's go through the concepts of the key concepts first. Right, so let's say you got the number, right? You got the final volume, but that's not what they want. They want the height, the new height over here. Okay, so so now you need to try to link it over there. So this is the part where no amount of general advice will help you. It's just, you need to be able to interpret what's going on. So think back at the physics. Don't get held up with the math or the algebra. You first have wine that is now increased or decreased. Let's see. Okay, so there should be two ways you can think about that. First of all, you can just intuitively understand that the temperature is decreasing, so the volume should decrease, right? Or you can look at the math over here. This is 10 minus 20, everything else is positive. So it's going to be decreasing. All right, so if this decreased, that means the airspace increased. That means the height would increase. So now you have a sense of how to tie that together, right? To tie your ultimate aim with what you have so far together, right? Your new volume to the new height, okay? Now you want to be more explicit. So let's do that one step at a time. So you can first go like, okay, I notice that if the volume of the wine change, that will have an opposite change to the airspace. Does that make sense? Okay, right, so what is my aim? My aim is to find H, which is part of airspace, right? So let me put that on the left. So the change in the volume of the air, so this is the volume of the air, this is the volume of the wine, right? The change of volume of the air is negative of the change in volume of the wine, which means change in volume of the wine is final minus initial. All right, so let me take off things I know. This I know, this I know, all right? So just to get some idea, I think I was solving this before. So this should be 746 milliliters. Final. So just to get a sense of that, right? So you know both of these, good. So now you know the change in air. So on the right hand side, technically you would just put what's the final? So 746 milliliters minus, let me factor out the milliliters, minus 750 milliliters. All right, so that's roughly 4 milliliters. So this is -4, negative, that's positive. And plug that in the calculator, it's roughly 4 milliliters. All right, how about on the left-hand side? Change of volume of the air, okay? So here you want to focus on, you want to try to link this to your aim, okay? So how can I link the volume of air to the variable H? Right, so now you notice that's a cylinder. So you can do it one step by step. The volume of the air, so volume of the air is in a cylinder. So what's the formula for cylinder? Volume of cylinder, well, it's the area times the height, right? So pi r squared times, so that's the base area times the height. Okay. So the radius of that air space and the height of the air. Okay, the base area doesn't change, the radius doesn't change, or the diameter doesn't change. So you can pull that out of the delta, like this. All right. And what is this? This is H new minus H old, right? Final minus initial. So whenever you see something starts to get out of hand, when the expressions get longer and longer, just calm down and go and check off everything you know. Because as soon as you check off things that you know, you'll feel much more solid. You'll feel much more on solid ground because you realize that, either immediately it solves a variable for you, or if it doesn't, let's say you have two unknowns, now you know where to go. You have an orientation of what to do next, right? So pi is pi, radius is essentially known, right? Half of the diameter. Do I know h nu? No, that's the variable, okay? Do I know h old? Yes, that's 1.5 centimeters. And I know the right-hand side. That's done.
Can you explain again how you got 746 milliliters?
By plugging in all these numbers over here. So, all right. So why don't we take 2 minutes, see if you get the same number over here. So see if you can fill in the blanks, fill in this part of the blank, and go forward and see if you can find h nu as well. So fill in the rest of this part. So for those who know what to do, go ahead. For those who don't, ask questions, ask away.
I have a question. So why can't we do just pi r squared times h, and then whatever we get for h, we can add to 1.5, since that's going to be the corresponding change in height for that volume, but then we have 1.5, so we add to it since we understand that the vapor is going to increase.
Sure.
Would you be able to do that?
Of course, yeah. It's a million ways to think about it. You can go forward, you can backwards engineer it, you can start from the end, you can start from the top, you can start.
Okay, one more question. So you found your answer for volume to be in milliliters, right? Mm-hmm. But earlier you converted your volume to be in liters. Does that have an effect on? No,
you just have to be careful with units. I was going to write this out as liters, but I was lazy and don't want to write 10 to the minus 3. Okay. But yeah.
I have a question.
Yeah, go ahead.
So the 750 times 10 to the negative 3 liters, that's the volume of the entire bottle, right?
That's the volume of the wine.
Oh, so it specifically says it's the volume of the wine?
Yeah, so that is one point where there's potential ambiguity.
Yeah, because I had this problem for homework, and I had to subtract the volume of that little part that the wine's not in, I guess, minus the volume of the bottle to find the volume of the wine.
Yeah, so this is the part where it's not really physics; it's just ambiguity in the English. But let me try to justify what their intention or their logic is. When you say you have a bottle, 750 milliliters bottle, let's say you go to Walmart and buy a bottle of soda and it says it's 2 liters. Does that mean a bottle is 2 liters, or does that mean you have 2 liters of drink? So hopefully the drink is 2 liters, right? It's the actual liquid. So that's I believe it's the intention behind that. Although it's even though so if you say buy a bottle of soda, it says 2 liter. It's a 2 liter bottle, but it's not the bottle. The bottle is larger than 2 liters. The amount of volume of soda.
So how do we know? Okay, because this is very similar to one of the questions I was on mastering. It's almost identical. And for that one, I did have to subtract the volume of that height, of the empty space minus the bottle volume to get the volume of the wine. So how would I know when to do that? And in this case, when not to? When to consider that to be the volume of the liquid itself?
To be honest with you, that is my answer is not coming from a physics answer. That is completely nothing to do with physics. It's how the English is written. I have 2 advice. number one is if this is purely a semantics issue, usually this is a completely legitimate question. You can raise your hand during an exam and ask. Okay? I don't know how this will work in online exams, but under normal circumstances, the semantics issue, which has nothing to do with physics, the questions you can raise your hand and ask. And an off chance that you ask and then you've misinterpreted it. It actually is a physics question, and the TAs or the proctors are not at liberty to answer you. The worst case scenario is they won't answer you, right? It doesn't hurt asking. My second comment is if you cannot ask, either, I don't know if the upcoming midterm can you ask questions or not. I don't know how that works. You have to email the professor and check what the rules are. If you cannot ask, make your best guess. That's the so use your best educated guess. What do you think the English means? That's the best I can do. Sorry.
Back to the context of what you were saying. If we were trying to, are we plugging in V initial to be in milliliters or liters, or it doesn't matter? Will just give us an answer in either milliliters or liters after we solve for the V.
All right. So I think we had enough time. Let me actually solve out everything and see if we get the same answer in case anyone has done this. All right. So clean this up a little bit. So I was at this step. So here I can write, move this over on the right, the plus wine, VI of the wine, initial of the wine, T final wine minus T initial of the wine. Keep in mind, there is a million ways to do this, to go about approaching any physics problem, and just sort of, and to be honest, if I do it, sometimes I might directly just skip to a middle step and go about it, just because I know I've done enough of these and I know what's going on. But whenever I don't know what's going on, so if I see a new problem that I cannot think ahead, then this is how I would go about it. It's just very step by step, sort of down to earth, and ask myself, do this first, and then write out the relevant equation, expand it out, check off things, write out the relevant equation, expand things out, check off the things, just follow these few steps, and usually it'll take me to where I need to go. So if your mind just immediately go, well, I can do this already, that's completely fine. And there's no reason to force you to think through the path that I'm going through right now. But since I'm writing it out here, well, this is the only time but forced to think this way is. But yeah, hopefully that makes sense. All right, so now I'm going to plug in numbers. Right, so back to your question of how to deal with take care of the units. This is my way of going about it. I always would change everything to base SI units first. Physicists love SI units, right? The international standard of units. So the punchline is this: if every number you put in is in base SI units, it'll come out as a base SI unit. That means you don't have to carry units in every line you write, right? That saves you a lot of time. You do all the conversion in the beginning and at the end. Well, you don't have to convert at the end, it's just the beginning, right? So liters is some, I always get confused, but I looked it up before this class. 1 liter is 10 to the minus 3 meters cubed in terms of the SI base units, right? So the initial is 750, just to emphasize that's initial, 750 times 10 to the negative 6 in terms of SI units, right? So negative 3 liters, just to be extra clear. This is the part where I won't write out on the left, and use orange. The parts that I won't write out in real life exams. 10 to the minus 3. All right, so you see 1 liter is 10 to the minus 3. So 1 liter is 10 to the minus 3 meters cubed, right? So that means this is 750 times 10 to the minus 6 meters cubed. So I'm just going to copy the part in front of any SI units into my work. All right, so let's see how this works out for me. And plus beta is 420 times 10 to the minus 6. VI, same thing. Maybe I should, since there's two of these, maybe I should factor that out first. So forgive me.
And we found that beta by multiplying the constant for water times 2.
Yeah. Sorry, he's trying to save a little time. Thanks for cutting. Yeah, thanks for catching me. Yeah, so sorry, can't resist. I'll do one step of algebra first, so I don't have to plug in too many numbers at the end. Right. Okay. So it's that times 1 plus beta and times T final. T final is 10 degrees Celsius. All right, here's another tip. Normally, the SI base unit for temperature is Kelvin. Celsius is just for human convenience. It's calibrated at the boiling point and melting point of water, which has no international, no universal significance other than humans drink water. But Kelvin has some universal significance, which because at 0 Kelvin, everything freezes and there's no more energy. Everything is completely, absolutely still. So there's a physical importance, significance there. So Kelvin is the fundamental unit that we chose to do physics in. So technically, if I follow my rule that I just said over here to the last dot, then I would change this to Kelvin and change this to Kelvin. However, this is a part where hopefully you've done enough of these problems that you know that a delta T, a change in Celsius, is the same as a change in Kelvin, because everything is just shifted by 273. Right? So difference are the same. Okay. So with that experience in mind, I would not change that. The final is 10 minus 20 with that. And I know it's going to work. But having said that, anytime you're slightly confused, when in doubt, always change things to SI base units. I guarantee you it 100% of the time always works. Of course, if I do it, it just slows me down. And I think at this point, the day before the exam, we hopefully know the change in temperature is fine. Yeah, but let me reiterate: if you just a general rule, when in doubt, change everything to SI units. It always works, right? Another advice is you can do your shortcut first in an exam, right? Do the shortcut first, get your answer. After you finish the exam, when you check your answers, and then now you can do it the longer way, right? Change everything and see if you get the same answer. If you have a spare 7 minutes at the end, may as well spend 5 of those to check one of the more complicated problems. That's an option. So let's see. Hold on my calculator. So I have 750 times 10 to the power of minus 6. I'm not going to plug all the numbers in for all the problems tonight, but since this is the first problem, let's actually do it out and see. 20 times 10 to the power of minus 6. If you don't have this, of course, your calculator might not look exactly the same as mine, but we hopefully know how to use calculator. Right, so 750, let me check, yep, right. Oops, what did I do? 10 minus, no brackets. There's a bracket. I'll do this one by one. 420 times 10 to the power of 6 times 10 minus 20 is negative 10. Right? So I have this plus 1, 2, 3, 4, 5, 6, 750.
Why am I cheating? Oops, sorry.
Oh, sorry, that's negative. It should be. So this part is 0.9958, and so 1, 2, 3, 4, 5, 6, right? So 746 times 10 to the minus 6, right? So that's where I got the 746 milliliters. Okay, and then moving on. So we had change in air is negative, change in the wine. So that's pi r squared, change in the height is minus the final wine minus initial wine. Right, so that is, the final is 746, the initial is 750 times 10 to the minus 6. 746 minus 750 is 4, right? So negative 4 is 4 times 6. On the left-hand side, pi r, so, okay, so here it's pi, this is 18.5 centimeters. So that's 18.5 times 10 to the minus 2, divided by 2, so that's radius squared, delta h. So delta h is h new minus h old is 4 times 10 to the minus 6 divided by pi 18.5 times 10 to the minus 2 to squared. The old over here is 1.5 centimeters. And therefore h new is, now I plug in the calculator, 4 times 10 to the power of 6, negative 6. Divide by 3.14 times 18.5 times 10 to the minus 2. Divide by 2, all squared. Okay, so that's that. And I need to add 1.5 centimeters. So did I do something wrong? The final answer would be 2.7 centimeters, in case anyone already got the answer. Square. Right answer? Just for your confidence, that number is correct when I briefly did it earlier, and this part, this should be the final correct answer as well.
I have a question.
Yeah.
When you said the delta change, or the delta change in volume for the height is equal to the delta change in the volume of the wine, where's the negative? Yeah, where's the negative coming from? Like, why do we put a negative there?
Oh, okay. So what's delta? So what's delta wine? change in y means it starts from here to here, right? It gets less, right? The volume.
Yes.
So what happens to air? The air gets
Has to increase.
expands.
Yeah.
Yeah, so the relationship, I'm translating that qualitative understanding into.
Oh, okay. So the negative is just simply because the wine is going to be decreasing. The volume of wine is going to be.
So imagine the volume of the wine went from 10 to 8. The volume of the air would go for, if that decreased by 2 units, that would, yeah. Hopefully
Oh, yeah. And okay, so you're able to set them equal to each other because if one decreases, the other one's going to increase, right?
Yes, that's right.
Okay, thank you.
Yeah. So this is the part of actually translating something from the physical understanding into something qualitative into quantitative, which is a key skill in problem solving. Okay. So in the spirit of just trying to solve more problems for you guys, let me move forward instead of checking my values, if that's okay with you guys. Okay. All right, let's do the next one, which is, oh, good, okay, humidities, yeah. Okay, so 34, so this is chapter 18, question 30, problem 34. Okay, so let's start from fresh. I will read it sentence by sentence. So the humidity of the room immediately, that's my room, takes me 1 second to draw. Volume is 440 meter cube. I love things when they're given in SI units. Is my screen still up? Yeah, okay. And at 25 degrees Celsius, T equals to 25 Celsius. Sorry, my computer is switching back and forth. And the humidity, okay, so humidity, if you study the chapter, you know, this is giving you, it's basically providing you this relative humidity. Okay, so I have all the information on the first line. I'm ready to move on to the second line. What is the mass of water and still evaporate from an open pan? Okay, so now this is an aim, right? It's asking for the mass of water evaporate, question mark. Okay, good. So that's technically all I need. And now the first thing I'll think of is what are the relevant equations or definitions in mind, right? Relevant equation or definition. Here's the part where I think there's a more tricky term here, relative humidity. I'll immediately translate that into something more tangible. So relative humidity by definition is, just to emphasize that, it's the pressure, is the ratio between the pressure and the saturated vapor pressure at that temperature. Okay. And if you ask how much water you can evaporate, that's basically asking how much water. So you have before and after. Before evaporating, after evaporating. After you evaporate, you want the new relative humidity to be 100%. So, for example, here, just quoting this won't give you any points, but if you apply it, it will give you points. For example, now you know that if I apply it to the original relative humidity, I know that, and usually this is given as well. So that means you can find the pressure initial is 65%. Let me write down the variables first. Initial times SVP, and final is RH final times SVP. So you know this, you know this, you know this, you know this. So now it tells you, without even going forward, you know the initial pressure and you know the final pressure. Right, so now you can go and...
Can you please explain what SVP is? What these variables mean?
Which one?
What's S?
SVP?
What's S in the, yeah.
SVP, saturated vapor pressure. That part I'll encourage you, it's a much longer discussion. I will encourage you to read the textbook. You need to know that. It means just roughly, it means the pressure of that room when it is fully saturated. Saturated vapor pressure. So it's the pressure of the room when it's 100% saturated at a given temperature. So,
okay, and we substitute. Go ahead.
Yeah, because when the temperature is different, you can saturate the room with a different amount of vapor, water vapor. So this depends on the temperature. It's a number that you look up from a table. So usually an exam will be given to you at that temperature. What is the saturated vapor pressure?
Okay, got it.
It's also, you can also see it from here, right? You see when the relative humidity is 100%, that's SVP. Does that make sense?
Yeah.
Yeah. All right. Good. So now just by writing out a definition, it already immediately spill out the initial pressure of my room and the final pressure. Final being it has fully evaporated all the water, right? So my goal now is to connect these new variables into this. So how do I connect pressure into mass? Now you can, if you've done a lot of these problems already before from your homework or discussion session and your own revision, you probably already know how to proceed. Let me just play dumb and assume minimum knowledge. How will I proceed? I will stare at P and V and T, and this immediately reminds me of a relevant equation. The ideal gas law, right? So immediately I will know, I think this is going to be potentially relevant because I just found P from something much more complicated, the relative humidity. It's probably more intangible. Now now you have P and V and T. The obvious guess is PV equals nRT. So that doesn't help you get any points. Make sure you apply it to this scenario. I'm not putting initial to R because R is a constant. It's a universal gas constant. So it's not going to depend on, it's just a number, right? Okay, so now that I've applied it to my scenario, I've found a relevant equation. Look, I immediately apply it to my scenario. Why do I apply it this way? Because I was given PI, right? So I should write out how does PI relate to everything. And I'm given PF, and I should write out how PF relates to everything. Now things starts to get out of hand. Let me do the same exercise over here, like check off things that you know and check off things that you don't know. Right, so TI, yes, I know it's 25 degrees. T final, it doesn't change. The problem didn't say anything changed. In fact, if you've studied saturated vapor pressure, you know these problems, you have to keep the temperature constant in order to solve it, or else it'll be more complicated. Right, so TF is actually the same as TI. If you want, you can write a note for yourself. And R, of course, I know. NI and NF, I'm not sure. How about VI and VF? What can you say about it? Stays the same, right? So you can make a note, or you can keep it in your mind. And PI and PF, you know. Look, I'm playing dumb, assuming I don't know where to go forward. I just follow, and I'm just looking at what's the most relevant equation given the variables I have at hand. It lead me to this. Immediately, it lead me to something else. It's solve NF. Hopefully now, it's much more obvious how, so it's getting closer and closer how you connect it to here. Yeah. Apologies to those who are way ahead of me and already know what the result is, but hopefully just these general tips are useful for you as well when you actually get stuck. So,
is S gonna be given to us?
Yeah, it has to. Yeah.
Okay.
Yeah, they have to. Right. So let me speed forward a little bit to conserve your time. So now, right, so I need to connect it to here. So I have the initial number. So think back to the physics. You have a room. What number are we talking about? Well, what pressure are we talking about? So if you're confused, what is this variable for? Look hints for other variables, right? What was it? This came from the P. What was the P about? The P was the pressure of the water while the room has this humidity. And P is the pressure of the water while the room has this humidity. So N must be the number of molecules of the water. Okay, so just water. So it's the initial and final number of moles of water in here. Okay, so how can I get water evaporated? Well, probably something like final minus initial. Then there's multiple ways you can go about it. You can, if you already know what to do, good for you. One way to think about it is backwards engineer it and think, okay, so I need the mass of the water evaporated. How do I get it? How do I relate that to initial and final? Well, that's the mass of the final mass of the water in the room minus the initial amount of water in the room, right? So if that is unclear, how to get that, how to engineer that on your own, you can actually draw a different diagram like this. Whenever you have initial and final, if you don't mind extra work, just a tiny extra work, you can draw, you know, like this. Okay, so these are water droplets. So final, you have much more humidity, initial, final, right? So you have more water particle here. So what is the water evaporated? So hopefully with a diagram like this, it's more obvious that if you have the final mass of water, but the initial mass, the amount that you can evaporate, the extra amount you can evaporate is just a difference. Right, so now your goal is how to connect this with this. And this is the part, you know, if you've done more of these, you'll know how to connect the molar mass to water. So these are very specific tips. I can't say anything. I can't give any general advice for you other than practice more of these type of questions. And I know this. This is also known, 18 grams per mole. Okay. All right, and not going to.
And the molecular gas, the molecular mass is going to be given to us as well, right?
Yeah, it should be. If I were to write an exam, I would. But the molar mass of water, hopefully you know, is 18 grams. You know how to figure that out if you know the periodic table.
Well, I don't think we're going to have a periodic table, right?
Yeah. So if you remember, if you know oxygen, and if you know oxygen is 16, it's the 16th element, you know, that will help you because H2O, sorry, the molar mass, yeah, 16 element. So H2O here, it's each of the H is 1 gram. The oxygen is 16 grams per mole. And, but that's a chemistry knowledge. That's not physics knowledge. So that's what I mean. A good, under normal circumstances, a physics professor writing a physics exam should not require you to know chemistry trivia. That's all right. How does this feel? Any questions about this? Mole, about units, mole is a SI unit, SI base unit as well. Grams is not, it's grams is kilograms is the base unit. So if you're plugging in, if you're using my method, this is what you want to plug in. You plug in this number from here, and then 18 times 10 to the minus 3 kilo in place. So because this is 18 times 10 to the minus 3 kilograms per mole. So anything with MKS, the other two that you want to know is temperatures, Kelvin. Moles is also a base unit for SI.
Sunny, I have a question really quickly. For the
I know that capital or lowercase n is number of molecules, right?
Yeah.
And then capital N is the mass of the total, or I keep forgetting the difference between the two.
Capital N or capital M?
N as in like Nancy.
All right, so yeah, let me explain that as well. The difference between this, well, this is exactly the same. Capital NK is the same as, this is literally equal, little NR. You can plug in numbers to check. Capital physicists, to be honest, physicists much prefer this version. I mentioned that in a few of my discussion sessions already. I'll repeat that. Physicists much prefer the left-hand side, because, again, moles are a human invention. It's how we conveniently measure. It's because we measure things in grams and kilograms, moles become convenient. Especially in chemistry, they adapt. In the past, the international standard was using CGS units, centimeters, grams, and seconds. The more modern one is MKS. That's why chemistry is sort of still stuck with the more old-fashioned system of unit. But if you measure things with gram, historically, then 1 mole of hydrogen atoms is 1 gram. Or you can reverse this argument, saying 1 gram of hydrogen atom, that number of hydrogen atoms, we'll call that 1 mole. So that's how historically you defined mole. It's purely because how we define grams as humans. It's nothing to do universally with physics. However, n is the number of particles. Every time I say this confuses people from chemistry, because physicists always talk about particle. So what is a particle in physics? In chemistry, you only hear about atoms, elements, compounds, molecules. You hear about these terms and you never hear, or rarely hear people talk about particles. Particle is any of the above. What do I mean? Anything that doesn't split up during the problem that you're concerned with, it's a particle. So if an atom on its own can be a particle, a molecule, let's say O2. So as long as within the problem, this O2 object never splits apart, right? So let's say you have a gas of O2. So you have all these O2s bouncing off each other, bouncing around, hitting, colliding like this. As long as none of them suddenly split up, and even if you do chemistry, you understand how much energy you need to activation energy you need to split up molecules. Normally in room temperature, you rarely split up a molecule. So if things don't split up, we call these particles, right? So it can be any of these. It's just physicists don't care about the chemistry of these things. They just blur everything together and say, we'll just treat everything like this. Okay. So if you think back in 3A, even when a ball rolling down the slope, sometimes we say there's a particle, right? Or projectile motions. You send a cannonball out, or a tennis ball, cannonball, bowling ball. As long as the ball doesn't split up, it's a particle. Okay. Does that make sense? So if you have a room of N2 nitrogen gas, as long as the nitrogen don't fall apart, N counts the number of particles.
Okay, that makes more sense. Thank you.
Okay, good. And to clarify, 1 mole is equals to an Avogadro's number of particles, right? Yeah, so is it 6 point, someone remind me, 26.02? Something like that. 10 to the 23. Is that right?
Yeah, that's right. 6.022. I don't know if that matters, but.
All right, good. Perfect. Yeah. Yeah, so this is the conversion. 1 mole is this number of particles. Right? So it's like saying 1 mole of There's a similar confusion. Just apply that to similar, right? So if I say 1 mole of N2 gas, how many how many nitrogen atoms are there? Well, there's 2 moles of nitrogen atoms, right? There's 2 moles of N, right? It's 1 mole of N2. So that's the same thing. If I say there is 5 N2 particles, how many N are there? How many nitrogen are there? Well, there's 10. If there's 5 N2 particles, then there's 10 N particles. It's the same idea. Instead of grouping things with moles, you're just literally grouping things in particles. Slightly more literal, right? You can sense my bias to physics.
Thank you.
Right. Yeah.
So Sunny, you said that the ideal gas law can be either written as PV equals nRT or PV equals nKT. When should we be using each version of the equation?
Whichever's, it's up to you. I don't have a general advice for this. I only have specific advice, and specific this depends on the convenience of the problem. So both works, just often one is more convenient than the other. For example, in this situation, if you know the molar mass of something, molar mass by definition is the mass of 1 mole of particle. So if I use capital N over here, I'll need to convert the mass of 1 mole of particles to the mass of 1 particle. So
okay, so for like a general rule of thumb, if we're given the number of particles, we should use nKT, but if we're given moles, it's more convenient to use the nRT.
Yeah, but in this scenario here, it's not given the number of moles, it's just asking for mass. So you need sort of a little bit of experience to so if you've done 5 of these problems, then you start seeing all 5 of them, it's more convenient with this, then you start to see a pattern and to develop that intuition. But yeah, if you, for example, if anyone insists on using capital N for this problem, then how do you convert from this step to the next step? The next step is the number of particles times the mass of 1 water particle, right? Don't put the mass of 1 mole of water particle. If you put N moles times mass of 1 mole of water particle, you get the mass of the total mass of the water. But if you use capital N, you're putting N number of particles times the mass of 1 particle. Then you get the total water particle. Right? So that's it. So I don't remember what is the mass in terms of kilograms. What is the mass, kilograms or grams or whatever. I don't know the mass of H2. So what is 1 water particle? It's H2O, right? So H2O doesn't break apart in this problem. So as a physicist, we just turn a blind eye to it and consider H2O as a particle, right? So I have no idea 1 H2O molecule, what is the mass in terms of kilograms or grams. However, I have a vague, still being a physicist, being extremely bad at chemistry, I have a vague recollection of the periodic table, which allows me to know, okay, it's what I explained, that how you add up the things to know that if I have 1 mole of water particles, then that is the mass of it. But if I have 1 more water particle, I don't know. But of course you can convert that. So if I know the mass of 1 mole of water is 18 grams, then the mass of 1 water, this is just a simple ratio problem, because the mass of 1 water is technically an Avogadro's of number. So it's 1 mole of, it's 1 mole times the mass of each mole, right? So it's Avogadro's numbers times the molar mass, right? So it's times the mass of 1 mole of particle. So it's 6.02 times 10 to the 23 times 18 grams. So that can't be right. It's the other way around. You also know, if you run into a trouble like this, you also know which one's supposed to be larger. This one is supposed to be larger. So I should be dividing by that. And So this is me saying it is possible, but annoying to convert between each. So if whatever's given that's more convenient, you can just use that. Yeah. So this side makes sense because the mass of one particle is supposed to be lighter than the mass of a molar particle, which is, you know, this 6 followed by 23 zeros number of particles. All right. Does that clear things up?
Yeah, that's good. Thank you.
Okay. Cool. All right. How do we feel? Do we want to switch and look at the practice midterm a little bit, or should we look at the other two? I'll put this on screen.
Can I ask a general question really quick
Yeah.
before we get into like any other example? I'm really confused on like entropy change for an adiabatic process, right? So I understand that, like, let's say for like the Carnot, is that how you say it? The Carnot, like a Carnot cycle? Is
That's a silent T.
a Carnot. Okay. Yeah, that. I understand the change in entropy is 0. And I know that, like, in the test, like when we were going over the midterm, for the adiabatic processes within the cycle, the entropy was said to be 0, right? Because in an adiabatic process, your change in heat is 0. So that makes the whole entire thing 0. So I had a discussion with the professor, and I was having a bit of trouble, like, understanding when, like, an adiabatic process has an entropy of 0, because she said that doesn't apply to every, like, every adiabatic process. So she said that some adiabatic processes can have a change in entropy, and I'm really confused with that.
I'm not aware of that.
Yeah,
I might be missing something, but
yeah, because there was an example in the, sorry.
Did she give a concrete example?
No, she said she was gonna like try to put it on Piazza, but I don't think she did. I think she forgot or something. But it was an example in the book where it was saying like, oh, like you go through an adiabatic process, right, where you expand a gas from like volume 1 to volume 2. And it was like, okay, calculate the change in entropy. So when I originally said 0, because I thought change in entropy for an adiabatic process was like 0, because there's no heat being exchanged. But the way the book approached it was that they used an isothermal process to kind of explain the change in entropy. And that got me really confused, because I just assumed that for every adiabatic process, the entropy change would be 0.
Sorry to bulge in, guys. I think question 5 on the practice midterm addresses your concern in that question. So I think Sunny, if you go to that question 5 on the practice midterm and address the Carnot engine and the change of entropy with the graphical, that would be helpful to all of us.
Yeah, I understand that part. It's just I completely understand with like that problem on the midterm, and completely would agree on it. I just don't agree. Well, it's not that I don't agree. It's just I don't understand one of the problems in the book where the change in entropy for an adiabatic process isn't 0. Yeah. So that makes complete sense to me. That question makes complete sense. It makes complete sense why an adiabatic process will have 0 change in entropy. So I don't understand like why in the book they would use an isothermal process to explain that change in entropy.
Yeah, so for your question, I don't know the answer to that. But since we brought it up, maybe someone else is interested in question 5 as well. This is relatively simple. A little quicker. So for Carnot engine, the first thing I would do is, this is the part where your studying comes in. You need to know how Carnot engine behaves. It's isothermal, adiabatic, isothermal, adiabatic. Adiabatic is steeper, right? Isothermal is gentler. That's how you draw it, okay, on a PV cycle, on a PV diagram. Just to fill in a little theory, remember PV equals NKT. Any ideal gas satisfies this. When you have isothermal, everything here is a constant. So P equals to a constant over V, right? So this you have, what you have is PV equals to constant, or P equals to a constant over V, like that. So you have something that looks like this. Right, so this y equals to 1 over x looks like this. what if I increase this to y equals 2 over x? Does anyone know how that looks like? The larger this number is, you basically just push this curve higher. The lower that number is, you push it lower. And that's why this constant depends on t. So as you see the higher temperature, you have a higher inverse, these are called inverse functions. You have a higher inverse curve. A lower temperature, you have a lower inverse curve. How about adiabatic? Adiabatic, you can't play, although this equation still works because it's always you're always treating this as an ideal gas. So this equation still works. The ideal gas law always works for the Carnot engine. However, the temperature is not constant. When you see that you're going from a high temperature to a low temperature in adiabatic process, because you're restricting you're expanding the system, right? From VB to VC, from B to C, you're expanding the volume. However, you're not allowing any heat to go in. So what happens if you expand, you imagine a box of gas, you stretch it, will it get hotter or colder? It has to get colder, right? If you squeeze it, it'll get hotter. If you expand it, it'll be the opposite. So as you can see from the diagram, this brings you from a high temperature to a low temperature. And as a result, the temperature is not constant. You can go through a long derivation and derive this relationship for adiabatic process. And now, as you can see, gamma for a monatomic ideal gas is 5/3. For a diatomic one is 7/5, but usually you won't get that in this exam. Right? It's going to be the simpler case. All right, so the function, it's p equals to some constant divided by v gamma, where gamma is larger than 1. So this means it's going to be a curve that is, well, that's huge. It's going to be a curve that is not as flat as this, but it's steeper than this because of this numbers larger than 1. It's going to decrease faster than it should. So that explains why adiabatic is a steeper, or you can use what I just said, right? There's no heat in and no heat out. That's the definition of adiabatic. That means it has to bring you from a high temperature to a lower temperature. That means it has to go steeper this way. Okay? If it goes any shallower, it will be above my dotted line, not below. It will never go down to the lower temperature. So that's a little theory behind this. Any questions? Okay, continue. Okay, so going back to here. Going back to here, so I've drawn my Carnot cycle, Carnot engine. Okay, so that cycle. What does that? We found that this, so you can also copy this down. I like to have delta, as explained in my classes. What does that mean for the change in entropy? Okay, so aim change in entropy during one's complete cycle, so the whole cycle. Question mark. Okay, so. The first thing, relevant equations from this two ways. So immediately, I will probably go with definition first. The change in entropy, the definition is delta Q over T. Okay, so this is a definition for delta S, for change in entropy. Be careful, this is change. I'm okay with anyone who doesn't want to write a delta here, but if you don't write a delta here, you will run in trouble. That is wrong, because S is actually equals to K log omega that we have not covered in this course, but just to emphasize that it is something completely different, not delta S. Okay. So to me, might as well, if one side changes, the other side has to change. That just makes more sense that way. Okay, but for this particular problem, I like to backwards engineer it. I like to start from the end. So the change in here, S cycle is first you go from A to B plus, because entropy is additive. All right. Now AB, that means delta Q AB. I can use my definition now. Remember, so the first step, what I'm doing is sort of just backwards engineering it, expanding out this. And then now I'm going to use the definition. So here, technically I should write A or B. So should I write TA or TB? If it's a change in heat from going from A to B. It's a trick question, doesn't matter because it's isothermal, same temperature, so TA and TB is the same. In fact, let's write TH. Plus BC. Now this is slightly curious what you should put there because the temperatures are not the same from B to C, but let me move on first. CD temperature, this time it's the lower one because CD is isothermal. Delta Q, dA. Again, this is going from D to A. Again, the temperature just raised, so it's a bit, it's not clear what you put T. It's clear to me, but you guys haven't learned yet. So, but it doesn't matter because this is adiabatic. Adiabatic by definition means this is 0. So it doesn't matter what you put, as long as you're not dividing by 0, which is true because nothing is at absolute 0 in this engine, otherwise things don't move. So as long as the bottom is not 0, the denominator is not 0, the top is 0, it's gone. So you don't have to answer that question of what should I put here. As a result, you have this. Okay, so now you need to get the signs correct. So from A to B here, is heat added to the system or
Sorry,
leaving the
study.
system?
Should that be delta QCD over TL?
Yeah, thanks. Yeah, the isothermal bit, thank you.
Thank you.
Yeah, and then now you need to ask if the heat is entering the engine or leaving the engine. So from here to here, the temperature is staying constant, as you can see, but what is the volume doing? The volume is expanding. So the heat, do you think, are you adding heat to it in order to achieve this or removing heat? You're adding heat, right? In order to expand the volume. So this is symbolically how people usually write it. If you look at a textbook, this is the notation. They draw this. Usually they imagine that this is the engine, and then so you'll see this diagram basically. So, so the total entropy, change in entropy of the engine, right, for one cycle, at first you add certain amount of heat to it. And then in the second part, you're going from C to D, right? Notice you're going from C to D, the volume is decreasing. So you're squeezing it, so what happens to the heat? Remember, this is isothermal, so you're not allowing the temperature to drop. So if you try to squeeze a gas, it's going to heat up. But if you need to keep the temperature constant, the only solution is you keep extracting out the heat. You allow the heat to release from the system. That's why people like to draw it like this. You see the heat enters the system on top and it leaves the system or the engine. By system, I mean engine in this case, at the bottom, right? So you subtract the amount of heat that is left, let's call it QL, over here. So that's the logic there, which means now you can make use of what's given over here. You can rearrange this, right? Delta QH over TH is equals to delta QL over TL. That means the second term is the same as the first term. Right, so back to Alejandra, I think you were asking what's going on with adiabatic. Adiabatic, by definition, means no heat in or out. Isothermal means temperature constant. Isobaric means remember barometer is measuring pressure, right? Pressure constant. And isovolumetric or isochloric, depending if you want the Latin term or the more modern term, is volume is constant. So there are these four processes that are popular.
Okay. May I ask? I know I ask a lot of questions, but like,
Yeah,
can
go
I ask
ahead.
another really quick question? So in the problem, they give us that ratio where it's QH over QC is equal to TH over TC.
Mhm.
The way it's presented in the book, it's like the other way around. So the way it's presented in the book, it's QC over QH is equal to TC over TH. Is that like the same thing?
Let me ask you this. If 2 over 3 is equals to 4 over 6, is that true, first of all?
Yes.
Is 3 over 2 equals to 6 over 4?
No.
You sure?
Oh wait, yeah, sorry. Yeah, sorry.
Yeah, there you go.
Okay, so they can be used interchangeably.
Yeah,
Yeah, I just
so
wanted to make sure because I'm like, wait, I used this one for my homework and I got it right. So I'm like, are they the same?
yeah, so just the beauty of equations means if something is equal on both sides, and if you do the same thing to both sides, they have to equal. It's like apple equals apple. So if you take a bite out of both sides, you still have an apple without a bite, right? So that's the
Yeah, that makes sense. Okay,
so
thank you so much.
yeah. So if you reverse the both sides, so it's the same. So that's how I think about equations. I probably could have given a slightly simpler example, something like this. And we flip it, 2 over 1, 4 over 2, right? So it's the same, yeah. Okay. So since we are on this, although I understand it seems more logical to go through maybe one or two more popular practice midterm problems. However, it seems like we're on the topic of Carnot engines. Do we want to do this problem instead? How do we feel?
I thought since the professor said that the type 3 questions won't be on the midterm. I don't
What? The
know,
what? Three?
category 3 questions.
Oh, is this a that it is. Okay, I see. Yeah. This one, I haven't, for preparing for tonight, I haven't solved it through, but just looking at it, it actually goes through everything about isothermal, volume, pressure, and internal energy. It deals with the first law as well. It seems to touch on a lot of topic. Maybe because it's touching on everything at the same time. That's why it's level 3. Yeah, but let's do a vote actually. Let me launch this on Zoom. So if you switch to Zoom, you should see a poll. Let me give you 30 seconds. Do you want to do a practice midterm problem, or do you want to do, say, this 2020? Okay. If you guys don't mind, let me use the restroom first. I'll be right back in 30 seconds. Okay, wow, that's close. Okay, so it seems like practice midterm wins just a little bit. All right, let's find out which problem we want to do in practice midterm. Let me create another poll. Let's see. Okay, so we have question 1, 2, 3. while I set up this poll in your mind, think about out in the practice midterm, which question or problem do you want to see the most?
Oh, I have a quick question about the midterm.
Yeah.
So it says available at May 1st at 1 p.m. to May 1st at 4:30. Does this mean that we can start, does this mean we have to start the test at 1 or can we start it at like 3?
No, you need to start at 1.
Okay, thank you.
I don't know what happens if you start later than that, but if I were you, I won't test it.
Okay.
Okay, all right. So in your mind, think about which problem you want to see. Let me just save this and launch. Yes. So we have done problem 3 in every single class in the discussion session. So I'm not going to include problem 3 as a option here. Let's see, how do I launch number 2? Here. There we go. And we just talked about question 5, right? So I'm just going to do 1 to 8 without 5 and problem 1 and 2 as an option. Give a few seconds to put in your notes.
Sunny, can I ask a quick question since I can't stay the entire time?
Yeah, go ahead.
I got, so whenever like when you do like a buoyancy problem, like let's say like you have like a piece of wood, or like in the case of this midterm where like somebody jumps in the water, right? And they're asking you like how much more like lead you can add, or like how many, you know, like logs of wood can you add like on a raft or something, right?
Mhm.
For it to completely sink. When you're doing that formula, right, where like you do like the buoyant force minus like, well, you're basically adding all the forces that are on that object, right? You
Right.
have to consider like the buoyant force of the of the lead as well, right?
Mhm.
Okay, I just wanted to make sure like I did that right, because I got the answer right, but I don't know if like, because she did it a completely different way. She did it everything in terms of density, and I do it the way like you help us out, where you know you write all the forces acting on the object.
I'm
So
glad.
I wasn't sure if that's like what she was also doing, and I just wanted to make sure for like that particular problem, we also have to include the buoyant force of the lead.
Right, yeah. You should, I think it actually give you a hint to say, yeah, that's in the end, take into account of the volume of the lead weight and note, or not explicitly, yeah, but yeah, you should, yeah.
Yeah, okay, I thought that's what I meant too. Okay, thank you so much. Have a good
Okay.
day.
Yeah, by the way, before you leave, so here's the poll results. So it looks like problem 1 and 2 are the most favorable. So for those who can stay for another 30 minutes, I'll finish off these 2 problems. So it will be recorded. If you cannot stay, you can check out the recording anytime tonight. Okay?
Thank you.
All right, have a good night. Okay, so for those who can stay, we'll finish our problem 1 and 2. Let me start with 2 since it's more voted. Okay, I'll try to do this with less commentary as well, so I'll go through it a little bit quicker. And so feel free to interrupt me and ask questions that you need to ask at any time. Just get my screen cleaned up. Okay. All right, so here we go, problem 2. So I will start here. You get home one day, your roommate is ill. Okay, I can't draw that. And has a dangerously high temperature of 106 Fahrenheit or 41 Celsius. In order to quickly reduce the temperature, clean up the bath. Okay, now I can draw something. So you have a bath, presumably with water, and you put your roommate in there. And what I need to label is the temperature of the roommate. Presumably there's temperature of the water, which is going to come into relevance as well. So I don't want to just write T, I will write TR equals 41 Celsius. There's a typo here, missing a degree Celsius. In order to quickly reduce its temperature, you put in bath of 8 liters of 8 liters. So volume of water is 8 liters. And temperature of water, as I expected, it's relevant, 25 degrees. Again, they forgot to write degrees. All right, is that all the information? Over here, yellow, there, put in the bathtub. Okay, good. So now I'm down to my aim, right? Part A. What is the mass of the water in the tub? Okay, so mass of water in the tub in terms of kilograms, okay? Question mark in terms of, good, SI base units, perfect. All right, so we can focus on this. So remember the strategy we talked about? The strategy is think about any relevant equations or relevant definitions, okay? I need to somehow link these three variables to this one. Out of these three that is given, which one's the closest to here? Probably not temperature, right? Now you're narrowing it down to volume and mass. That should remind you maybe density is relevant. So density, what is the definition of density? So definition of density is mass per unit volume. And this is perfect because remember, now you need to label things because this won't give you any point, but if you say water, this will give you at least 1 point in setting up in a hypothetical paper exam, right? So now the next thing is you can check off things that you know. Do I know volume? Yes. Do I know density? Yes. It should be given in real life in your exam. The density of water in SI units is 1,000. It's very easy to remember for fresh water. That's 1,000 kilograms per meter cube. You see, when I remember these, sometimes people ask me, how do you remember all these different numbers or like different trivial numbers? Because I don't remember units. Every number I remember is in SI units, SI base units. So if I need, so I remember the number, and how do I figure out the units? Well, this is the definition. I just need to remember what is the SI unit, base unit for mass, kilograms. What's the SI base unit for volume? What's MKS? How do I make up volume? It's meters cubed, right? So this has to be kilograms per meters cubed. Right. All right, so moving on. My aim is to find mass of water. So that's density of water times volume of water. Density of water is 1,000 in my natural units, and volume is 8 times 10 to the minus 3. So this can be converted to 8 times 10 to the minus 3, right? So if it's an SI units, I just not write it all together. It's if you have noticed everything I've done before, you'll notice that all the units I write is the ones that are not SI unit. If it's SI units, I try to make things as simple as possible. And so this cancels out. So that means it's left with 8. And now that you guys are more and more familiar with my way of doing my strategy of approaching these things, I have 8 as my final number. What is the unit for this final answer? Type it out in the group chat. Let's see if people understand how I'm doing these problems. Perfect, Rachel, you win. There you go, kilograms. Right. That's part A, done, easy. Let's move on to part B. That is the correct answer, by the way, just to give you confidence. Now we move on to part B. Sometimes you need to draw a new diagram for part B if anything changes to the situation. Sometimes you don't. Let's see. If the situation doesn't change, we don't have to redraw things. So what is the mass of ice you would need to add to the tub in order for your roommate and the water to reach an equilibrium? Okay, so let's do it bit by bit. Mass of ice you would need to add. Okay, so I'm adding ice. I do need to add, change my diagram. Actually, I don't need to change it. I just need to add a second part to my diagram. So this whole thing is now, there's a before and after, right? So this is before and after. I'm adding ice. Okay. I could have drawn more ice cubes, but I just need symbolic to capture what I made over here. So I won't be drawing things very realistically, as long as I can capture the fact that I've added ice. Okay, and then in order for roommate and the water to reach an equilibrium. Good. Okay, so everything at the end, the temperature of the roommate must equals to the temperature of the water in the tub, must also equals to the new temperature of the ice. Of course, the ice is going to melt first, but because you've added that should be accounted for as well. Should all equals to T final, right? They should all come into equilibrium. So equilibrium means everything has to be the same at how many degrees? 37 degrees Celsius. All right, normal body temperature, that's perfect. All right, so I have everything up to here. Once the ice is entirely melted, yep, that presumably is going to be melted. I'll keep the diagram clean. Calculate the mass. Okay, so that's my aim. Part B. Mass of ice in kilograms. So mass of ice equals question mark, brackets, I want it in kilograms. That's it. That's all I need. Let's finish the sentence, assuming that it's initially, okay, so initially T initial of ice is 0 degrees. And your roommate has the mass, okay, the mass of the roommate is 70 kilograms. Okay. Notice how I immediately not write the kilograms because that's SI units. For reference, here are some of the specific values. Okay, let me just copy over here so I don't have to look up again. So I'm given C naught. C of water is 4186. Now, should I copy the units? I won't, because look, joules is SI units. It might not seem like it, but if you remember, something like newtons and joules, something like this, these are just lazy way of writing out a long SI unit. For example, newtons is basically, so 1 Newton is basically a kilogram meter per second, right? So Newton is basically a lazy way of writing out all this. How about joules? Joules is for energy or work, right? So work is force times distance. A simple one is that. Force is newtons. Distance is meter. So 1 joule is basically 1 Newton meter, right? So it's basically 1 kilogram meter square per second squared. So joules is just a lazy way of writing something that's SI base unit. Now, if you have something like millijoules, you need to take care of the milli. If you have something like kilojoules, you have to take care of the kilo. But if you have something like joules, that is completely made out of MKS. There's no extra factor of 10 to the power of 3, there's no factor of 10, no factor of 100 in front of it. Okay? So that's the reason why on this side, I don't have to write that, and the human body, so C of the roommate is going to be 3470. Okay? So everything else is in SI units, and I'm confident that I have all the information. That goes away. Okay, so here, we're ready to solve this. Now, same strategy, think about relevant equations or relevant definitions, okay? Hopefully the relevant definition, I don't think there's anything I need to define. All the variables are temperature, mass, volume. It's pretty straightforward. Maybe the relevant equation that comes to mind is like Q, the change of heat is MC delta T, right? So you'll probably recognize this as some heat loss, heat gain type of issue, type of problem. So we can start, right? So delta heat gain must equals to the total amount, the absolute value of that must equals to the amount of value lost, amount of heat lost. Okay. So what's gaining heat in this scenario? So how many things do we have? We have first the roommate. We have the bath water. And we have the ice. Let's analyze them one at a time. So at first, the roommate is going to be warming up or cooling down. So you look at the numbers over here, the roommate went from this to this, meaning the roommate is cooling down. Okay, so the cooling down means you want MC delta T. Immediately you want to label things as well, right? It's because you have different mass going on and different C going on, delta T. Let's actually skip one step just to save a little time. T final of the roommate minus T initial of the roommate. Okay. So this is the part, this belongs to Q loss, right? So this is losing heat. Okay. Let me just use an arrow. So this is the roommate's losing heat. This is going to go on this side of the equation. Next, the bath water. Water. Okay. What's the water going to do? Is it going to warm up or is it going to cool down? So you look at the numbers over here and it warms up. Perfect. So water, water, T final water minus T initial water, and it's going to warm up. So this will go on this side. It's going to gain energy, gain heat energy, right, from the roommate. The roommate's going to lose energy. The water is going to gain energy. So this is going to go on the left side. This is going to go on the right side. And finally, we have ice. So, oops. So for ice, of what's going to happen to the ice? Well, the ice is a little bit more complicated. You know why? Because when you put the ice in there, you can think about first, does it gain or lose heat? So the ice starts off at 0 degrees and it ends up with 37, right? That's what happens to the ice. So it's clearly gaining, but first it has to melt. So it has to first melt and then it has to warm up. So melt means mass ice. So melt means M times L, right? L vapor fusion, right, of ice, plus, and then warming up. Now you can use the warm up formula, which is MC delta T, so final of ice. The C here, now it became water. So you can just put CW, right? It's the C of the water, and TF minus TI of the amount of ice over here. So therefore, let's put everything together. Does the ice go on the left-hand side or does it go on the right-hand side? Does this process, is it gaining heat or losing heat? So it should be gaining heat. Right? So to melt it, it gains heat to melt and then it warms up. So both of these has an upwards arrow. So all this, and this has to go, or basically all these has to go on this side, all of this has to go onto this side. All right, so on the left, we have M water, C water, T final. Let me just write T final because all the T final are the same. T initial water plus M ice, L fusion of ice, plus M ice, C water, T final minus T initial of the ice. That's the left-hand side equals to the right-hand side, which is M roommate, C roommate, T final. The final is, everyone is the same, so I'll just write T final, and the initial of the roommate. Okay. Let me use and copy this to a new page. Another tip, guys, for this online exam particularly, have plenty and plenty of scratch paper ready. You don't want to halfway through your exam, you don't have enough scratch paper to work with and you have to look for new paper and then responders might not like it. So get an abundance of scratch paper. All right, so, wow, this looks complicated, right? So remember, when you have a long expression like this, what do? You go and make it simpler by checking off things you know. All right, so let's see if we, by muscle memory, we can remember what we know. Let's start from the very left, mass of the water. Am I given the mass of that's the bath water, right? I don't remember actually, let me check the diagram. Yes, it is 70 kilograms over here. Okay, So that's a tick. Might as well just put that in. I don't know. Let's tick off things first. Right, C of water, we do. Let's just tick off all the C's because that's known. Final temperature, yes. Remember that? 37, right? So final temperature, they all have the same final temperature. Good. Initial temperature of the water, anyone do remember? Do we have that? I do. So yeah, it starts up at 25. So we do know that. What else? All right, mass of ice. No, I don't know that. In fact, that is the goal. That is the aim, right? So I'm not supposed to know that. I'm not supposed to know that. Latent heat of fusion of ice, we should be given. In fact, I'm confident that it has to be given in order to solve the problem. But let's just move on first. Temperature of the ice, initial temperature, do you remember that? Yes, it's 0 degrees. Yeah, so we know that. Mass of the roommate, do we know that? Mass of the roommate. Oh, sorry, mass of the roommate is 70. All right, so how about the bath water? The bath water is here. I see. So yes, it's 8 kilograms, but yeah, we do know. We do know both. Okay, so we know the mass of the roommate. Just be careful that it's not the mass of the roommate, that is the mass of water. And how about the initial temperature? Yeah, he was at 41 Celsius, so we know this. But so as you can see, the problem has to, you have to know LF as well. Is it given explicitly? No, but in the midterm, these have to be given. All right. Let me pause for questions. Need I go further? Catch up on the chats. All right, looks like we're good. Oh, the absolute value signs might be confusing. So we need to be careful when we plug in the numbers. Let's actually plug in the numbers. 8, 4186, was it? 4186, yeah, 4186. Final of the water was 25, sorry, no, 37. It's body temperature. Minus initial, that's 25. Plus, all right. So you see that when you have absolute value signs like this, first of all, you can distribute the absolute value signs into each of them because each of them are always positive. Now, you need to be careful which way around of this it is. You need to make sure everything is positive. So 37 minus 25 is positive, so that's good. So next is M ice, latent heat fusion of ice. Let's find out what that is. Latent heat of ice. 334, yeah. As you see, it's SI units. If you Google something, everything usually it's given in SI units as well. You can see over here, 334 joules per, oh wait, hang on, joules per gram. Oh, okay, so you need to be careful about that. So it's given in 334 joules per gram, right? So 1 gram is 10 to the minus 3 kilograms. Okay, so it's 334 divided by 10 to the minus 3 joules per kilogram. So 334, so it's underneath, so it's 10 to the power 3. Okay. And then mass of ice, C of water, 4186. Final temperature, 37. Initial temperature of the ice, 0. All right, so now you have to check, is this positive? Yes. Is this positive? Yes. Is this positive? Yes. Okay. On the right-hand side, mass of roommate is 70 kilograms. That's 3,000 something, 3,470. And the final temperature is 37, minus initial temperature is 41. Right? Is this positive? No, so you need to flip this, actually, to ensure this is positive. Okay, any questions? If this is confusing, please ask.
Where did you get the 3,470?
From the given.
Oh, okay, sorry.
Let's pull that up in here. Yeah, any other questions? If you're confused with the sign, please ask. All right. So hopefully you see how this proceeds and solves. All right, so let's go to the next one. And we'll do the last one of the day, problem 1. Okay. So it says a scuba diver and her gear displays a volume of 80, right? So we have a scuba diver and her gear like this. Displays a volume of 80. Let's just treat them as a system, right? As a particle, as we physicists call it. And have a total mass, so the whole volume of this whole system is 80 liters. You see I write down liters because that's not SI base unit. And have a total mass of 65 kilograms, mass 65. What fraction of the volume is displaced when she entered? Okay, so that part is the aim, but let's read the final part first. We'll come back to the aim. When she entered the water and is in equilibrium. Okay, so fraction of volume displaced. So presumably she did not fully get submerged into the water, only partially. So that's how we get a fraction, right? So this volume, we should be careful. This is the total volume of the scuba diver plus the gear. Okay, the total is right. So in equilibrium, now that the density of water. Okay, so we'll copy out the information as well. Density of water is seawater is 1.025 times 10 to the power 3, so that's 1025 kilograms per meter cubed. That's SI, right? The aim is to find the fraction displaced. Cool. Question mark. Okay. Any questions so far? Okay, so now we can focus on this. So again, so remember what is the strategy? Hopefully by repetition, this is getting more and more, well, on the one hand boring, but on the other hand more familiar. You look at your aim, you look at what's given, you ask yourself what are relevant equations or definitions that connect these, what's given to what you need to solve. Okay, so it's hard to say. This is a little bit tricky over here. I don't recall in the back of my head immediately a formula that connects fraction. So one thing is we can pick one of the variable and try to expand it out first into something more tractable. We'll pick the most complicated one here because there's no point expanding mass or volume, but maybe we can expand that. So what do we mean by fraction displaced? Well, the fraction displaced is how much volume that is in the water, so the volume that is submerged, over the total volume of the scuba diver and the gear, right? The total, the scuba diver plus gear, right? That's the fraction. All right, now I can have something. So in order to find this, in fact, if that doesn't make things easier, tick off things that you know, check off things that you know. Right, so do I know the volume submerged? No. Do I know the total volume? Yes. Perfect. So you see how this system works. Immediately you've narrowed down from finding this to find this in this. Okay. Hopefully in your head now, bell starts to ring and you see, oh, volume submerged. I know, there's the buoyancy formula. And that involves this number, that involves this variable. Maybe I can connect it to anything that is given. Okay. You see this is a strategy of going, this is basically using the backwards engineering strategy and starting from the end and trying to expand the end and try to meet the beginning from the end. Sometimes you start from the top and you meet the end by expanding from forward. Okay, so All right, so how do I connect this? Well, there must be something to do with buoyant force. There's a system to deal with force. In last week's tutoring center, we talked about how to deal with forces. So it's very simple. You draw out every single force that is relevant to the diagram. You ask yourself two questions. Question one, what is touching the object? And question two, what is not touching the object? Anything that is touching the object will give rise to a force, contact forces. And anything that not touches the object and still give it a force is the non-contact forces. So what's touching the my blob over here? Just to throw out questions to keep people awake. Right, so there should be water. Perfect, thank you, good job. So the water, what force would that provide? Water will provide a buoyant force, right? So which direction? It points up. Okay, so start all the forces from the center of mass and draw it pointing up. Right? So that's the first force. I'll label it B. And then what else is touching my scuba diver and her gear? Nothing else, right? It's only, you see only water touch this part. Well, technically air. The only force I know air will do is air resistance, but I don't think it's gonna be relevant here. So I'm done with all my contact forces. I'm sure that I haven't missed anything, and I'm sure that I haven't included anything that doesn't exist. How about non-contact forces? The only non-contact force you ever learned so far is gravity. Perfect, Jessica, good job. So gravity provides a weight. Okay. There you go. All right, so now you go about and think about Newton's second law. That's the steps. If you have watched the video from last week, I basically go through how to approach any force problems. Number one, draw a free body diagram, ask these questions. Number two, Newton's second law. Number three, expand the variables. Okay, I'll show you what that means. Newton's second law tells me that if this is in equilibrium, there was a keyword in the question as well. What fraction of the volume displaced when it's in equilibrium, right? So equilibrium means that B has to equal W. Okay? So that is my second step done. My last step is to expand out these variables. What is the buoyant force? Well, if you have studied, you will know this is rho VG, right? And try to label things as well, right? So what is the rho? Rho is the rho of the seawater, C. And V is the volume, not the volume total, right? Because be careful, which one are you going to plug in, the total or the submerged? But only the submerged is going to be relevant for the buoyant force. The part that is above is not going to provide any buoyant force. Technically, it's in air. Air provides a little bit, but it's 1,000 times smaller, so I'm not going to worry about that. And expand, so I've expanded out this side, expand out this side. Do you know the formula for weight? Hopefully by now you would. MG. The question is labels. Labels, labels, labels. Always very important. What is the mass over here? The only logical choice is the mass of, because, well, it's the weight of what? The weight of the scuba diver plus gear. So it's the mass of the scuba diver plus gear. So it's the total mass over here. All right. Now, what can you do? Check off things that you know, right? Gravity, you know, actually the gravity cancels, so that's fine. Density of seawater is here, that's done. I don't know this. This is technically canceled out. Do I know the mass total? Yes. Perfect, it's done. Right. So if you want to see more details, discussion of that, check out the video from last week, where I go through all the force, basically this procedure in more detail. You see, you follow the procedure. I love solving force problems because if you follow these 3 steps, you guarantee to get an answer. It solves itself, basically. So it takes practice. Don't get me wrong. I'm not saying that immediately anyone will immediately do this, but it'll give you a very good guideline of how to do it. And if once you're familiar with it, takes you solve these kind of problems a few times, maybe like 5 or 6 problems in down the road, you will get master it right away, and it'll solve itself every time. All right, so that is my part A done. Oh, yeah, it's not completely done. Well, this has to plug in here, and you plug in everything, hopefully. Do I need to go further, or are we good? No objections? All right, move on. Briefly, explain why the diver will float on top of the water, include any calculations needed to support. Okay, so part B, the aim is why float? All right, this sounds like a very qualitative question. We want to translate that to a little bit more quantitative. Well, what does that mean? Well, if it floats, the first hint is it's in equilibrium, but that's not enough. Because if it's in equilibrium, Newton's first law says that an object will stay at rest if it starts off at rest, or it will move at a constant speed, right? So if it's at equilibrium, but if it's always if that's all you know, if you start moving downwards, then she's not going to float. She's going to move downward at a constant speed. The fact that it's constant speed is not going to be helpful to the diver if she wants to float. Right, so equilibrium is a good start, but not enough. So what we want to understand is if the scuba diver is now underneath the water, will she keep falling down, or will she start floating up again? So what is the situation after she's underwater? Well, let's analyze the force diagram one more time. So the contact force is the seawater, that's the buoyant force. Okay. But this buoyant force is not the same as the orange one that I drew up there. So let me put a prime. This is the new one. Because you're more submerged, you have more buoyancy. So that's a different one. However, the weight is going to be the same. Right? So as a result, in this case, let me put W prime. But W prime is the same as W when B prime is larger than B. Therefore, in this case, the forces do not balance, right? So over here, you see the old B is equals to the weight, but the new B is not going to equals to the weight because the new B is larger, right? So in this case, let's write down Newton's second law. So it says MA is equals to all the forces. So it's B prime minus W. So mass, whose mass? Well, if this is the total weight, I should have the total mass, the buoyancy. So maybe another way to say it is scuba diver plus gear, the acceleration of the scuba diver plus gear, the buoyancy of the scuba diver plus gear, weight of the scuba diver plus gear. Okay. But now we're sure because remember the old B is equals to weight. So B prime is larger than W. So the right-hand side is going to be larger than 0. That means A is going to be larger, the scuba diver plus gear is going to be larger than 0. That's a positive number. So since I've defined B as positive and weight pointing down is negative, so positive is going up, you see the acceleration is accelerating up. So anytime she is submerged, she feels an acceleration that pushes her back up so that she floats. Okay? This is the comprehensive answer to this. If this is remember this practice midterm was designed as a paper exam. If you've written anything probably less than what I discussed, this whole answer that I discussed, probably you'll get full credit as well. Probably we're not that concerned with that problem. The more emphasis is in part C. But yeah, I've given you the full answer if you want to analyze this quantitatively. Any questions for this so far? Going a little fast, but hopefully we're still following. Well done.
Could you also say that this diver and her gear are just less dense than the water?
Yes and no. ultimately, when you say that, I think you'll get full credit. From physics, if I'm being a very physics point of view, stepping into like a proper shoes of physicist, that is, we love to question everything to the root until you have a very fundamental answer. So imagine, so I could ask you, why does if the density is less, why does it? If the density is less than the water, why does it flow? Then you have to answer that. Okay? So the questions never end. It's like how parents always get annoyed with like 10-year-old kids where keep asking why. And physicists are like that, and we want to answer why the universe works the way it is, and we try to trace things all the way to the most fundamental things. Acceleration is very fundamental. Remember 3A. What do you learn in physics 3A? First thing you learn is displacement, velocity, acceleration. These are motion, how things move. So if things float, it doesn't necessarily mean it's less dense. And things float, it just means that it's it's going up. So having said that, usually I think whoever's grading this, including myself, we're not going to be that picky to write density is less. That's true. But I'm just, if I'm being picky, one can ask, well, okay, why density less means flow? Okay. So these are the type of questions that annoy parents. But now you know why. The blue part on the bottom right corner is exactly why. It's because the force of buoyancy, the B prime, is larger than the W prime, which means if there's an unbalanced force, by Newton's second law, there's an acceleration that goes up. Yeah. There's a little bit of philosophy chat as well, just to get a break from the physics before I do the final bit of part C, just to catch my breath as well. You might wonder, okay, it's never ending if you keep asking why. At some point, does it go circular? Like, well, then you can ask, well, why is Newton's second law true? Right? Things like this. So, from a philosophical point of view, if you keep asking why, yes, of course, at some point, things will be circular. Asking why is apple red, and then you say, well, it's because it's an apple. Things become circular. So at some point, to solve this issue in physics, you'll need a starting point. So you need something called fundamental laws or axioms or postulates, the similar meaning. So you start from a law, and then you explain everything else. Okay. So Zoom just flashed on me. I hope I'm still here. Okay. Yeah. So when you say density, when the density is less than the density of wood is less than the density of water, so it floats. That's not a law. That's not a universal law. Newton's second law is much more fundamental, because Newton's second law explains everything about motion on Earth. Anytime you want to know how things move, Newton's second law explains. Whereas the trivia, let me sort of exaggerate and call that the trivia of the fact that density is less will float. This is true, but it comes from something more fundamental. It's not the end of the story, and in fact, it's just more like a human experience that we know it to be true most of the time. But in principle, I can conjure up situations where it's not true. If the density is less than water itself. Okay, here's a quick example, which actually relates to part C. It's a good segue. Now, let's say I have the scuba diver and the gear, and now I attach a lead weight. Is this going to float or sink? I'm going to attach, I don't know, I'm going to make up a number, 2 kilograms. What density are you going to calculate? The density of the scuba diver, the density of the gear, or the density of the lead? Are you going to take an average? You add them and divide by 3? No, that's wrong, right? Are you going to do a weighted average? Yes, technically, if you do a weighted average, that will be correct. So what you need is let's say this is 2 kilograms, and what was the mass of the 65 kilograms. So technically, what you need to do is, this is much more important. So you do 65 over 67 of the density of the scuba diver plus gear, plus 2 out of 67 of the density of the lead, and compare this combination with the density of the seawater. You see how complicated this becomes. So if you know what to do, that is true. However, hopefully this is a convincing argument that, on the other hand, if you analyze the force on here, and now you draw all your forces, okay, I have one force going up, one force going up, one force going down, one force going up, one force going down. Let's say it's very complicated, okay? Force A, B, C, D, E. So now you add your force A plus B plus B minus E minus E equals to MA. Okay? Ask yourself, is this positive or negative? If it's positive, it means acceleration is going up. If it's negative, acceleration is going down. That makes sense? Is that a good
Yes,
argument?
thank you.
It's a long way to explain that, but yeah, hopefully just a little break from the math. Let's finish this off. Well done, you guys, for staying all the way, by the way. We'll be very close. All right, how much mass lead weight are we adding to this? Right, so okay. Diagram, how much that will have to, how much weight I have to add to the dragging belt in order to sink to the bottom of the ocean. Okay, so this is my new diagram. I want the scuba diving gear as a system, and then add some lead weight over here. Okay, and all the previous information should be the same. That's 65. The volume is 80 liters. And the lead is M lead, which we don't know. And in order to sink to the bottom, take into account of the weight of the lead, and density of lead is density of lead is 1.13 times 10 to the power of 4. All right, so I have all my information here. And let's begin. Let's see. So the aim is precisely this. Right? Just for, I can write this out a little bit more explicitly. 11300. So that's 1, 2, 3, 4. Yeah. So you see, then you can compare with density of water, which is the seawater 102. So you see that that's larger. Just to get a feel of it. Even though I say that's not a good argument to argue why something sinks or not. All right, so let's solve this. Okay. All right, do we remember what the strategy is? So we wanted to sink, right? So it's a force problem. So we go with drawing all the 3 steps, just to recap. Step number 1, free body diagram. Number 2, Newton's second law. That's MA equals to all the forces, and add up all the forces, and then expand the variables and calculate whatever you need to calculate. Okay. To do that, ask yourself, what's touching? It's not touching. So draw all the forces starting from the center of mass. What's touching the system? This time, treat the system as the whole thing. Okay. The water is touching the system. The water is touching the scuba diver and the gear. That's going to create a buoyancy force for the scuba diver plus gear. The water is also touching the lead, and the questions say take into account of that. So that's going to create a buoyancy for the lead as well. Okay. And then that's all that's touching it. This time air doesn't even touch it. Right? So going to non-contact forces. The non-contact force, which is gravity, acts on the scuba diver plus gear. The gravity also acts on the lead. All right, there we have it. We have our formula. Now we move to the next step, Newton's second law. So there's two ways to think about this. There's a more direct way, and there's a more sort of just dummy way, just to grind through this machine, right? Once you learn that this machine works, technically you just have to grind through it. I'll show you how to grind through it first. So if you don't want to think, you just want to shut up your brain and grind through this, all you have to do is write down Newton's second law, which is, let's call going this way positive, right? So it's B of the gear of the scuba diver plus gear plus the buoyancy of the lead minus this minus this is equals to the mass of the whole system and the acceleration of the whole system. Right? Okay, so you want this to sink. That means you want the acceleration to be negative, right? So you want A of the system to be negative. This means, right, so if you want this to be less than 0, multiplying by the mass is also less than 0, you need to solve this equation over here. B plus B minus W plus W is less than 0. You need to solve that. Okay? But of course, that leads to B of S plus G plus B lead has to be, if I move these terms to the other side, you'll see this has to be less than S plus G. That, which makes sense because you just want this to be larger. You just want these to be larger than these. So that's my quick way. If you don't, so if you're not a machine just to grind through the steps, if you grind through it, that's very good training, to be honest, because it will work for every single problem. But at some point you get lazy and you go like, okay, to sync, I just need these larger than these. So you can directly start with this step to make sure these are larger than these. Okay. So I would say this part is, let me call that optional step. You can directly start with this blue step over here. And for the optional gray step, my personal feeling is if you're not familiar with this system, I encourage you to use it over and over again so that you familiarize it, so that solves all your future problems that have to do with forces. By the way, which after the midterm, we will learn a new non-contact force, not only gravity, we will learn a new force, it's the electric force, and one of the few other non-contact forces in the universe that actually can act a force on something without touching. Non-contact forces are very fascinating, very mysterious. It doesn't touch things, but it still exerts a force, if you think about it. So after the midterm, basically you do a lot of other forces problems as well. So if you master this, you're in luck, because all you have to do is in the future, you just need to add a new type of force to your free body diagram. It's the exact same procedure in solving these. Right, going back here, what's the last step? So I'm done with that. The last step is to expand out my variables. All right, so rho S plus G, rho VG, right, plus rho VG equals mg plus mg. So you see that how confusing it is if you don't label things. So we have to. So this is the volume of the scuba diver plus gear. This is the volume of lead. Mass of the scuba diver plus gear, mass of lead, and all the G's cancel out. Nice. And what next? While I'm copying this to the next page. So this is the final time I'm going to say this tonight because it's the final problem before I leave you guys to study for tomorrow. When you have a complicated expression like this, how do you make it simpler? It's probably like the 10th time I've done it today. You check off things that you know. Okay? So hopefully you have this. This is the last time I'm going to say this, and hopefully this will stay with you and help you, really help you for tomorrow, right? So let's check off things. Yes, I know this. This is 65. No, I don't know this. In fact, that was the goal, right? To find the mass that actually helps me sink it. Yes, I know the density of lead, which is the 113 whatever, 11300. Density of S plus E, I don't actually know that. Volume of S plus E, yes, that's 80 liters, right? Yeah, 80 liters, I believe. Yeah, so I should have copied liters over here. Yes, so I know this is 80 liters. So if I plug it in, that's the number I plug in. Then the density of lead, I don't actually, sorry, volume of lead, I don't. All right, now we are faced with a problem. We have one equation and three unknowns. So this, and this. So now the only hope is you find two other equations to link these together, because you cannot solve one equation with three unknowns. You can solve three equations with three unknowns. But these are all to do with like volume and mass and density. So probably what comes in mind on the side you can add is, I know density of S plus G is the mass of S plus G over volume of S plus G. Okay. And the density of lead is the mass of lead. And hopefully, after solving so many problems, you'll see the benefit of actually writing out labels. Because if you don't write out label, you just write rho equals to M over V. That doesn't really help you. Now you can go and tick off things. So do I know this? Yes, this is 65. Do I know the volume of S plus G? I do, yes. It's 80 times 10 to the minus 3. So this will give me this. One down, one to go in order to solve lead. Right? So here, what do I know? Do I know the density of lead? Yes, I do. Do I know this? I don't. That's the goal. Now, this means I can't actually solve this from here, but I have two equations and two unknowns. So technically, I can stop here. Of course, that won't satisfy you. I'll do one more step. Two equations are unknown. You just substitute away things you don't like. My ultimate aim is to find the mass of lead. I don't really care for the volume of lead. Let's get rid of that, right? So the next step you would write is, this is density, right? Density is mass S plus G over volume S plus G, S plus G, plus the G, the gravity cancels out. Lead, volume of lead, we'll substitute away the volume of lead, which means exchanging this mass of lead over density of lead. Oh, sorry, hang on. This is what happens when you sew for 3 hours. This should be the water, seawater density. It's the fluid that causes the buoyant force. Let's see. Which is something we do know. Not lead, but right? Mass of S plus G plus mass of lead. Okay. And now let's do a final check. Yes, yes, 80 times 10 to the minus 3, 1025, 1025, question mark. Yes, 11300, yes, 65, question mark. And now so let's move things to, I could stop here, but might as well. We've done so much. Move this to this side, lead M S plus G minus C S plus G. Here you can factor this out, right? So it's mass of lead, rho of C over rho of lead, minus 1. S plus G minus rho C. So finally, you see where this is going. Mass of lead to be there you go. Okay, so everything on the right-hand side, you just plug in the numbers in orange that I've written up there. This looks a little bit weird. Why is this less than? It's because over here, is the density of C or lead, which one is larger? Density of lead is larger, right? So what, on the denominator, when you take that fraction and subtract by 1, are you going to get a positive or a negative number? So here, you're going to get a negative number. So in order to make it negative, there's a better way to do it from this step. I'll write it out in a second, but I can fix it here. Is if you swap the order over here, you swap the sign of equalities as well. Don't swap the top though. Rho C, S plus D, 1 minus rho C, rho lead. So just to double check over here, this is positive. Just to check over here, this is positive. And then here, let's just check the top. This is density of S plus D times the volume of S plus D. So since this is larger than this, the scuba diver is denser than C. So this should be positive. Okay. So now you have the right signs, and that you need the mass of lead to be larger than this number in order for them to sink. Okay. So if you want to avoid having that in this step over here, do an orange, you could have, instead of move things to the other side, you should move these to this side. Then things would be more intrinsically positive. So for example, on the right-hand side, you have M lead plus, I won't do the whole thing, but just lead, and lead. And then move these to the other side. So you have rho C, let's take over here. Did I make a mistake over here? Yeah, I need to put the top as well. But if you plug in the numbers, trust me, it'll make sense. I'm doing things in a very abstract variables, but they should match. So if I had done the more sensible way on the right, that would be cleaner. Or if you work with numbers, actually. All right, so that is the end of this. Don't be afraid of the algebra, because when you plug in the numbers, it's much more concrete than the abstract bit. Hopefully this was useful. All right, any final questions? All right, if not, thank you very much. Well done, guys, for staying for 2.5 hours. And hopefully this is useful, and hopefully this is helpful for you tomorrow. I wish you guys all the best. And yeah, you guys are very welcome. literally wish you guys all the best for tomorrow, and I'll see you guys in the next discussion session. Okay, goodbye. Have a good night. The recording is going to be on the cloud, by the way, and it should be accessible to everyone. Okay, goodbye.